there is one celestial object that dominates our skies. A star that shines so brightly it drowns out the light of all other stars in the universe. That star is, of course, the Sun.
We're just past the summer solstice, and here in Britain the sun is above the horizon for 16 hours every day.
So it's a great time to get outside and see the sun, and ask a few questions. Where does it come from? How does it fit into the universe? And what, if anything, makes it unique?
Welcome to the Sky at Night.
Welcome to the Bayfordbury Observatory, part of the University of Hertfordshire, a place where astronomers are looking at stars similar to our sun.
Tonight we're journeying out into the Milky Way in search of a new perspective on our brightest star.
We'll be exploring the previous lives of the sun, looking at how the stars that came before it form much of the material that now makes it shine.
And could life exist here on Earth only because the sun is an unusually quiet star?
Also, what is springtime on Mars like? Or midsummer on Venus? Lucie Green tours the solar system to see what seasons are like on other worlds.
At almost 90 degrees, the planet is effectively orbiting on its side.
Plus, stargazing in the daytime, the treasures of the night sky that you can see even while the sun is up. But first, to the sun itself. Our sun's what's called a yellow dwarf, pretty average as stars go in terms of size and mass, and neither exceptionally hot nor spectacularly cool. And it's now settled into a fairly comfortable middle age. It formed more than 4.5 billion years ago from a large cloud of gas and dust. Most of the cloud became the sun, with the remnants evolving into the planets and the rest of the solar system.
The sun is enormous. You can fit 1.3 million Earths into one solar volume. It shines because of the massive temperature and pressures at its core. This drives a continuous nuclear reaction, converting hydrogen into helium and releasing huge amounts of energy.
This nuclear fusion creates more than 600 million tons of helium every second, along with plenty of light. Light that our eyes soak up as sunlight. A little later, we'll be using a telescope here to take a close-up look at the sun.
But first, the Earth's orbit isn't perfectly circular. This means that the distance between the sun and the Earth varies throughout the year. So you may be surprised to know that now, at the height of British summertime, we're about as far away from the sun as we'll get this year.
In fact, that change in distance isn't nearly enough to account for the seasons that we experience. So what does cause summer and winter? And what would seasons be like elsewhere in the solar system? Lucie Green investigates.
To understand how seasons work right across the solar system, a good place to start is with our own planet. The Earth's seasons are driven by our relationship with the sun and the way the Earth hangs in space. But the most important aspect is that the Earth is tilted. As the Earth journeys around the sun on its yearly orbit, it spins on an axis that runs from pole to pole. But the whole planet is tilted over. It's a phenomenon known as axial tilt. The Earth's axial tilt is 23.5 degrees from the vertical. And for me, that doesn't feel like very much, but actually it has some dramatic consequences. Consequences that drive change across the planet. To see why, I'm going to recreate the solar system right here at the Royal Observatory in Greenwich. This is the Earth, of course, and the lamp here represents the sun. Now, because the Earth is spherical, that means that the sunlight falls with different intensities on different parts of the globe. Towards the top, the sunlight comes in at an angle, so it's more spread out. Towards the middle, the sunlight's falling directly on the planet, it's more intense, and those regions get hotter. but the Earth is tilted. So that brings the UK and the Northern Hemisphere into a position where it's pointed towards the sun and it's receiving more sunlight than in the south. So for us, we have Northern Hemisphere summer, and for the opposite part of the world, they have winter. Now, the Earth's tilt doesn't change, well, at least on the timescales that we're interested in, but our position in space does. As we go on our journey around the sun, we reach a point where neither hemisphere is looking directly at our local star. Now sunlight is falling over the equator, and we have autumn and spring. This is the equinox. Fast forward 3 months, and we come around, and we find that we reverse our initial positions, and now the southern hemisphere is pointed towards the sun, and they have summer. And so it goes on, orbit after orbit, running through the seasons. Our tilt and changing seasons have an important effect. They regulate our temperature, stopping any part from getting too hot or too cold. And we've learned that the tilts and the seasons of the other planets in the solar system can be very different to our own, and that leads to some interesting seasons on other worlds. Venus, our next-door neighbour and second planet from the Sun, has virtually no tilt, although, curiously, it rotates backwards. The absence of an axial tilt means that there's always more sunlight falling on the equator on Venus than there is up towards the poles, and that means there is no seasonal variation on this planet. Mars is about 1.5 times further from the Sun than we are, which is part of the reason that temperatures on the red planet rarely get above freezing. But with a tilt of 25 degrees, its seasons should be similar to ours. And indeed, we do see changes. The polar caps shrink and grow, clouds of carbon dioxide form at the poles, and winds pick up, sometimes creating huge dust storms visible from Earth. But there's another factor that affects Mars's seasons. Its orbit around the Sun isn't circular, it's an ellipse. And that means that there's a 43 million kilometre difference between its closest point to the Sun and its most distant. This makes Mars's northern summer longer than the southern summer. But there is one planet that stands out from all the rest. Uranus has the most unusual axial tilt in the whole solar system. At almost 90 degrees, the planet is effectively orbiting on its side. And that means that when it's summer in the northern hemisphere, it's constantly bathed in sunlight, whilst at the other pole, it's plunged into a frigid winter when the sun doesn't rise for decades. But this planet has an extraordinary variability, and as it moves on in its orbit around the sun, it reaches equinox. And at this point, there is 8.5 hours of sunlight and 8.5 hours of darkness all over the planet. It takes Uranus 84 years to orbit the sun, which means each of its seasons lasts 21 years. To find out what effect its bizarre tilt has on the planet, I'm meeting Uranus expert Patrick Irwin. Now, Uranus is a very different planet to our own world, isn't it? And the most detailed view we've had of Uranus was with the Voyager 2 flyby in 1986. Now, what were the seasons that were playing out when Voyager 2 got there?
At this moment in time, the South Pole was pointed almost entirely towards the Sun, so we're southern summer solstice.
And this is what I really want to know. What are the consequences on a planet's seasons if the axial tilt is at 90 degrees to its orbit around the Sun?
The poles actually receive 50% more sunlight on average over the year than the equator. So the equator gets kind of cold, whereas at the pole you'd expect it to get very, very hot in the summer and very, very cold in the winter. But in fact, what we found was that if you look at the temperature all the way across the planet, the temperature at the South Pole was almost exactly the same as the temperature at the North Pole. The temperatures everywhere were the same all over the planet, and that was a big surprise.
So the pole that's in sunlight was the same temperature as the pole that was in perpetual darkness?
Yeah. A good analogy is kind of like a black ball going around the sun, and the sunlit side's going to get very hot, whereas the winter side's going to radiate heat away into space and get very cold. If you took a ball of metal and did the same thing, then the heat would arrive on the sunlit side and be just efficiently conducted through to the dark side.
So the fact that Uranus is this gas giant is absolutely fundamental to this very uniform temperature that it has.
That's right, that's right. I mean, it's the atmosphere is free to move, not just at the surface like it is on the Earth, but it's free to move within the entirety of the planet.
Now, it's been almost 30 years since Voyager 2 flew past and saw this very plain planet. What's been happening since then?
And what we found was actually Uranus is actually a lot more interesting than we thought it was. This was measured in 2004, and the equinox was in 2007. There's a very bright band of cloud around the southern pole. And then with that, there's these small discrete clouds, which we believe are clouds of methane. And it seems to be that as the sun comes around to the equinox position,
Which is what we have here.
Which is what we've got here. The north is getting more and more sunshine, and the south is getting less and less sunshine, and that makes the atmosphere unstable.
So I suppose this perhaps sluggish character of Uranus and the fact that it took quite a while to see these changes is an artefact of the 84-year length of Uranus's orbit. And it just means that you have to study Uranus for much, much longer.
That's right, yes.
Well, Pat, thank you very much, and thanks for bringing these fantastic images.
My pleasure.
Here at Bayford-Bree, they have 11 telescopes, and they're run by Mark Galloway. He's going to train one onto the Sun to reveal a familiar feature that we're beginning to see on other stars too: sunspots. How's it looking, Mark?
Well, we've got a little bit of cloud, but
Ooh,
it's looking pretty good.
yes. So quite a bit of turbulence.
Yeah, that's just the atmosphere boiling. Like you see in a hot bow during the summer's day. You
And
see,
twinkling stars as well.
And twinkling stars, exactly the same effect. So this is an image in a particular part of the spectrum called hydrogen alpha. And here we can see a pair of sunspots. Sunspots always come in pairs, and they appear as dark spots on the surface of. But the interesting feature here, which often associates with sunspot, this is a plage, and this is slightly above the sunspot, and it's a lot hotter, which appears bright in H alpha.
So we can see sunspots on our local star, but I assumed it's not possible to see sunspots on other stars because they're too small to get that sort of resolution?
Well, most stars no. Okay, but particularly here at Bayford-Bree, where we look at very, very small stars called M dwarfs. Now, what we do in those is we do something called photometry. So we look at how the light varies, and when the sunspot comes into view, the light will dim, and we can see
So
the
it's
sunspot.
a darker patch on
Yes.
a bright surface, so you'll get less light.
Indeed. But unfortunately, that's exactly the same kind of thing which we see in the exoplanet trend. So,
Of course, yes.
Yeah, so we have a technique to distinguish the two. What we see is the sunspot appear, as here,
Okay, yes.
and then disappear as the star rotates. And what we see is we see a dip in light.
Oh, yes. But that signature looks very much like an exoplanet.
That transit, exactly. However, if we looked in the hydrogen alpha band, we've got the same animation. Because we've got this bright layer on top of it where the plage is, we actually see, instead of a dimming, we see a brightening.
So even though the sunspot's dark, the Laplage is light enough to make the whole thing come up.
Yeah, that's exactly it.
And are we finding many spotty stars? Are most stars spotty?
Well, we don't really know. This is one of the reasons why we're doing this long-term monitoring, because we want to select candidates for exoplanet surveys that aren't spotty. But they might be going through sunspot cycles like the Sun is, which means we're going to have to look for these things for a very, very long time before we get any real results.
So watch this space.
Indeed.
Coming up, I'll be asking, where does our sun come from? But first, here's Pete Lawrence with his guide to how you can stargaze in the daytime.
The 22nd of June was International Sun Day, when astronomical societies in over 20 different countries took part in a global solar observing event. So I've come to Regent's Park in London to join a troupe of fellow sun gazers.
It might seem a bit strange, the concept of daytime astronomy, but you certainly shouldn't write it off. There's plenty to see up there, for example, the most obvious thing being the sun, but of course you've also got things like the bright planets and even the distant stars.
When observing during the day, you need to look after your eyes and never look directly at the sun without protective equipment.
One of the objects which is synonymous with nighttime astronomy is the moon, but the moon can actually be seen during the day and for much of the month.
During the day, the moon appears as a lovely blend of soft blues and whites, making it look eerily transparent. And it's easy to see lots of surface detail with great features on view through a telescope.
Now, at first glance, you might think that's it, but there is another object which can be seen with just your eyes when it's in the right position away from the sun, and that is the planet Venus.
Venus is incredibly bright, allowing it to cut through the blue haze of the daytime sky. And depending where it is in its orbit, it can appear at different phases, from a full disk through to a thin crescent.
And with a telescope, other worlds can be seen too. Now, sadly, Jupiter is a bit too close to the sun for comfort at the moment, but when it's further away, it is possible to see it even in the daytime sky. And amazingly, it's also possible to see surface features as well. Features such as its candy-striped weather patterns, the Great Red Spot, or even shadows cast by 4 of its largest moons. And what about further afield? Now, if you know where to look and you've got a telescope, it is possible to see even bright stars during the day. Now, at this time of year, I'd recommend looking for bright stars such as Arcturus, Sirius, and Regulus.
And now I'm going to have a go at finding Regulus. The trick is to start by aligning the telescope with the sun.
I've set these setting circles on the telescope mount to match the coordinates of the sun. And what I have to do now is basically turn the telescope so that those setting circles read the coordinates of Regulus in the sky. That should just about do it. So if I'm lucky, then what I should see is the bright dot of Regulus in the field of view of the telescope.
But the object that offers the most staggering views in the daytime has to be the sun.
This is a little bit different from the other telescopes out there. It's a pair of binoculars.
Yes, they're 20 by 80s.
Right, okay, so big binoculars. And of course they're fitted with solar safety film.
These are homemade things.
Okay.
It's a little bit of do-it-yourself, which is quite fun.
So what sort of things can you see through these?
Sunspots, had the neighbours come to look at it, even track the rotation of the sun with it.
Well, the filters are very, very easy to make, and if you want to make one yourself, then we have actually got some web clips up on our website where you can go and find out how to do it. That is absolutely brilliant, wow. So how was that actually taken?
A 4-inch refractor, got DSLR straight in prime focus.
So it's just a normal stills camera?
And with a webcam on, I achieved that.
Okay, so the sunspot there shows the dark portion in the centre, which is called the umbra, and then around the outside of that you've got what's called the penumbra. So is that your first webcam photo of the sun?
That's the first webcam photo of the sun.
That's really impressive.
Yeah, I suffered for that.
Now there's another treat in store in the sky this month, and one you don't need a telescope to see, and that's the focus of this month's Star Guide.
During July, you might catch a display of noctilucent or night shining clouds. Located at the edge of space, in a narrow layer 50 miles up, they form when water vapour freezes around tiny particles, such as those created when a meteor vaporizes in the atmosphere. From their viewpoint, the sun is still above the horizon, which is why they appear to shine. They may typically be seen a couple of hours after sunset, low above the northwest horizon, or a couple of hours before sunrise, low in the northeast. A bright display may remain visible all night long.
Next, it's a remarkable thought, but the material that makes up our sun has had previous lives. Much of the material in the sun was formed in other stars that then exploded, seeding clouds of gas that in turn became the nurseries for new stars. To find out how this cycle of star formation and death creates the elements that make us up, I'm talking to galactic archaeologist Sean Ryan. You know, it's hard to remember that we live in a very strange place in the universe, that everything around us is made of carbon and oxygen and nitrogen, these heavy elements, and even the sun isn't just pristine hydrogen. So where do all of these elements come from?
Stars throughout the age of the galaxy have had a key role in the formation of the elements that we see around us now. So if you go all the way back to the Big Bang, you had hydrogen, helium, and the tiniest amount of lithium being produced. Nothing else of any consequence. And so it's successive generations of stars where those elements have been produced. That production mechanism is one involving nuclear reactions. So a star starting off with a very simple composition of hydrogen and helium can work its way up to almost the full suite of chemical elements.
And all of this is happening at the centre of the star, and we need to get them out. And we've got a picture of how that happens here, and this is the Crab Nebula.
It's quite a challenge for that material to get off. So there's a range of masses of stars, somewhere between perhaps 10 times the mass of the Sun and perhaps 25, 30 times the mass of the Sun, in which stars can produce these heavy elements during their lifetime, eject them in a supernova explosion, and then they can be folded into the gas from which subsequent generations of stars form.
So what can we say about the Sun's predecessors? Can we write down the sequence of stars that have led us to the Sun?
Astronomers sometimes think of the Sun as being a third generation of star. They don't mean from that there were just 1, 2, 3 stars, but the very first stars came out of the Big Bang, if you like, of the first generation, made of almost pristine hydrogen, helium, and that little bit of lithium. Subsequent generations of stars, which would still be amongst the oldest in our galaxy, had a slightly higher content of heavier elements.
Which will have come from those first stars.
That's right. And then ultimately, once you get up to stars formed perhaps over the last 5 to 8 billion years, then indeed you find the kind of composition which we see in the Sun.
And so we've got this idea that by looking at the elements within a star, you can say something about its history. And there's one nice example of this. So this is a star called HD 162826, which I'm sure you're familiar with. But this was in the news because it was announced as a likely solar sibling, a twin of our Sun. So what does that mean, and why is it exciting?
We have a whole range of elements which we can observe in stars. So we can measure the composition of carbon, of nitrogen, of oxygen. And if you do a match between the measurements of the composition of this particular star, HD 16226, and the measurements we can make in the Sun, you find they're an incredibly close match. But more than that, this particular star also has the same motion through the galaxy as the Sun does, which suggests that they perhaps formed out of the same gas cloud, therefore giving rise to both the same composition and the same motion through the galaxy.
It's rather fun, and there must be more of them out there. Sean, thanks a lot.
Thank you.
There's been a lot happening in the solar system this month, and so it's time for some astro news.
I feel really privileged to have seen one of the transits of Venus. But this month there was a transit of Mercury, but it wasn't seen from Earth, it was seen from Mars, picked up by the Curiosity rover. Now we have some images, but don't be underwhelmed. This is the first one. Now, the two rather large sunspots are a distraction. It's X marks the spot. That is Mercury crossing the Sun. And just to show you it's a transit, here's another image. Now, what's exciting about this is that this is the first time we've seen the transit of another planet from another planet. Pretty unique.
Now, the mission I'm most excited about at the minute is Rosetta, which is on its way to comet Churyumov-Gerasimenko out in the outer solar system. It meets the comet in August and then will fly into the inner solar system, landing a probe on the comet's surface in November. So this first image is from April the 30th from Rosetta, and there's the comet. You can see it's this fuzzy blob. It's already showing signs of activity. But if we go to the next image, which was taken on June the 4th, you can see that that activity has ceased. The comet has gone back to a nice quiet state.
Yeah, the tail's gone.
Exactly, yeah, it doesn't look very cometary at all. So that's good news for Rosetta, which wants it to be nice and quiet when it arrives, so we can watch the comet waking up. But it's also a bit confusing. We're not sure why the comet would have shown activity and then quietened down again. It's these questions that Rosetta will help us answer.
But now, back to the Sun. It's often called an average star, but it's the only star that we know of that supports life. So what makes it so special? And what does that mean for the search for life elsewhere in the universe? I'm talking to public astronomer Marek Kukula. Well, one of the interesting things about the Sun is where life does exist. And we generally sort of look for life around other stars in the Goldilocks zone. We've got a sort of a diagram of that here. And this is where we find liquid water.
That's right. So this is the range of distances around the Sun where the temperature is just right for water to be liquid. So not so hot that it boils away as a vapour, and not so cold that it freezes into ice. And you can see that the Earth is slap bang in the middle of it. Of course, that's not the only thing that makes a planet habitable, because Mars and Venus don't have liquid water on them now, so there are other things going on. But certainly this seems to be the most sensible place to look for life, because we know that our sun, although it's a fairly stable star, has been increasing in brightness by about 10% every billion years. But also the sun has other forms of activity, and it spits out great clouds of material.
Now, speaking of stability, our sun can be quite active, and I think this is a dramatic picture showing just that.
Yes, absolutely. And this sort of thing is going on the sun all the time. This enormous prominence arching off the surface, explosive flares going on the surface. But some other stars that we know have planets going around them, we see activity which is 1,000 or even 1,000,000 times more violent than this. We call them super flares. And if one of those happened in our solar system, certainly it would be rather unpleasant for our civilization.
So the Goldilocks zone, it sort of lies between sort of Venus and Mars here around our sun. But how about on other stars? Is it likely to lie in the same place?
Well, depending on how bright that star is, the Goldilocks zone will be either nearer or further away from the star itself. So if you want to have liquid water, you kind of have to be in that regime. But then, of course, if the star is different in other ways, if it does have these super flares or if it has various forms of activity that are dangerous, then perhaps being in the habitable zone might be great for water, but it might still not be very good for life because you might be too close to where all of the nasty stuff is going on. So there are all sorts of different ways that stars can behave and misbehave, and we're not sure at the moment where our sun falls in that spectrum of behaviour.
Is it good or is it bad?
Absolutely.
Oh, I like that idea.
So what we really need now is a proper census of lots and lots of stars, thousands or even millions of stars, to find out what their general behaviours are so that we can see where the sun fits into that overall pattern. And there are things like the Kepler mission and the Gaia mission which are doing that.
So until then, we probably don't know if our sun is unique or not.
We know that our sun is special to us, and that's maybe good enough, but it would be nice to know how it compares to other stars.
Well, that's brilliant. Thank you very much, Marek. Last month, we asked you to join us on a hunt for asteroids that can collide with our planet. We think we know the position of just 1% of the asteroids that are close to Earth or cross its orbit, and we want your help to change that.
We had an unexpected delay in getting the site ready, but it's there now, and you can try and find an asteroid by going to asteroidzoo.org or to the Sky at Night webpage. And when we come back next month, we'll show you what results we've all managed to achieve.
But before we go, we've got one last treat. A few months ago, we ran a competition to give one of you the opportunity to select a location to be imaged by the Mars Reconnaissance Orbiter.
The winner was John Green, and he chose to image a region of Mars called Haber's Chasma. It's this canyon system here, just above the more famous Valles Marianas. And so his image has now been beamed back to Earth from the Mars Reconnaissance Orbiter, and here it is, this stunning view of wind-sculpted features. And so these long, thin ridges, which look good enough to walk along, are the result of the rest of the rock being scoured away by the action of the wind. But whatever they are, it's a beautiful image.
It is. I always think of the Martian atmosphere as quite thin compared with Earth, but the fact that it was able to do this is quite amazing. That's it for now. Next month, we'll be looking at Rosetta, the European mission that aims to put a probe on a comet and then follow it as it orbits the sun.
It's so exciting that Rosetta, after an 11-year journey, has nearly reached its comet, and we'll bring you some of the first images next month.
In the meantime, get outside and get looking up.
Good night.
And The Sky at Night, How to Read the Solar System BBC book is available now. Here on BBC4 tonight, though, we have a world movie premiere for you. Based on a true story, a woman gets a tantalising glimpse of another world in Swedish drama Everlasting Moments next.